And we're going to go get right into it today. I'm not going to tell you quite yet what the topic is. Do that later. Maybe you can come up with it on your own. I will tell you that it's going to be relatively quant heavy today. So that being said, the first thing we're going to do is I am going to put three quant questions at once on the screen. And we'll take about 6 minutes to try them. I'll kind of update you with some text on the screen as we go about how much time is left. You know, just attempt to solve them your best and don't post your answers publicly. Go ahead and just, you know, chat me privately if you'd like, if you have questions or you want to verify your answers, and I'll try to keep up. Let's take a look at these things. All right. So get some paper ready if you want, and we are off and running here if this will cooperate, which it doesn't want to do, of course. Give me 1 second. Let's try this again. Why isn't it going with me here? All right, I will figure this out in a second. I'll tell you what I'll do. I will just get to PowerPoint separately and advance the slide here and hope to figure it out as we go. Let's take a look at these three questions now. So there we go. Just a reminder, as we're going, don't post your answers publicly. I will update you with timing as we go. Let's go ahead and try to take 6 minutes to answer these things. I'll hop off video. All right, about another minute to tackle these problems. All right, there goes about 6 minutes. So some of those problems I think are kind of tough. I'm hoping to show you later or throughout this hour that all of them are kind of tied together by a single topic. Does anyone want to suggest or have an idea as to what topic might link all of those questions? You can go ahead and type this in chat. And if you're watching on the recordings, try to brainstorm maybe what could all of those questions had to deal with? Here they are again. Well, maybe something emerges as we start discussing. So I think there's a couple, potentially. Aaron, I'm not quite sure what you mean by scale, but certainly there is some kind of multiplication happening here, multiplying by some number to stretch a value. Maybe we'll see if something more clear emerges in a second. Gloria has suggested estimation and or smart numbers, and I would suggest that you can use some of those tactics here, but estimating in the second problem, all of these answers are so close together, it might be a little tricky. But I love the comments that are coming in, especially this idea of smart numbers for this particular problem. I think smart numbers would be a great way to handle this problem. I'm going to ask Gloria if she attempted or if anyone else attempted to solve this problem using smart numbers. And if so, what numbers were chosen? What numbers were smartly chosen? Because if you think about this problem, you don't really know how much money she's going to save each week or for how many weeks or total. But not knowing is actually kind of nice because it allows you to flexibly pick the numbers you're looking for. So suppose we said she was going to save $10 each week for a total of 20 weeks. If D were equal to 10 and the number of weeks W were equal to 20, you should be able to figure out how much money she's going to save total, right? 10 bucks times 20 weeks should equal a total of T dollars or $200. And now she's going to potentially change her weekly savings plan and the duration for which she saves. So we'll call this we'll just call it like D prime, the second number or value for how much she could save each week. And it's supposed to be 30% more than before, right? She's increasing by 30%. So I like this. We could bump this up 30% of her original 10. Well, let's see, 30% of 10 is 3. So the new amount she's going to save is 13 bucks. She's going to decrease the number of weeks by 30%. Think about now how many weeks she'll be saving if she was saving for 20 weeks before. 30% of 20 weeks. Well, 10% of 20 is 2, so 30% should be 3 times that, 6. And so she's going to decrease her number of weeks by 6 down to 14. So now she's saving more money per week, but she's saving for more weeks. Let's see what that total gives us. That should give us a new total. 13 times 14, you can do a little number crunching there, should end up with 182. So clearly it's less than original, right? So she clearly doesn't save more or the same amount. She doesn't save 109% or 100%. She's going to save 182 out of the $200, which should break down to 91 out of 100, or 91%. Now, I think smart numbers is a great way to go about doing this. And if you were choosing smart numbers, you could have chosen some different ones. $10 a week for 10 weeks might have been even easier. And smart numbers is really safe here. But I think we could also do this one algebraically and still end up with the correct answer of C. And it's this algebra that I'm trying to relate all of these questions in that set to. So we'll do this in a different color. T, we know, is equal to D times W. And the new amount, the new total, is going to be equal to the new amount of D, the new amount of dollars per week, times the new amount of weeks. If we can relate the new D to the old D, we can say, well, hey, this new amount is equal to the original plus 30% of the original. The new W is equal to, well, it's 30% less than the original. So W minus 3/10 of W. You could then multiply these through and get something that looks like this. It's a 0.3D. You could FOIL that through. Of course, it might even be easier to then extract on the left, on the right side, factor out a D from the first portion and factor out a W from the second component. Now take a look at this. Let's bring the D and W to the front, which we remember is T. 1 plus 0.3 times 1 minus 0.3. Anyone recall what this template is? Because this is the thing that's going to link our problems today. This is the difference of squares, right? It would FOIL into 1 squared minus 0.3 squared. And let's go ahead and do that over here. 1 squared minus 0.3 squared is 1 minus 0.09, which is equal to 0.91. Now, I'm not saying that you would go about doing this problem recognizing the difference of squares and doing it that way, but you could. And the difference of squares is a single topic, but it's one that the GMAT can kind of drop into problems a lot of different ways. So normally we think of the difference of squares as kind of this construct involving a couple of variables. It's a plus b times a minus b, which FOILs out into 1 square, a squared, minus a second square. And so you often see that in kind of, you know, these type of problems. You recognize relatively immediately that, oh, I'm going to have to deal with some difference of squares stuff here. I should factor out the numerator and the denominator into pieces that look like this. and then solve the question. So we could try doing this. Let's take a minute and try to do kind of one of these classic difference of squares problems. Try to beat me to it. I'll start doing some stuff on the screen. Try to beat me through this problem. And if you finish, you can go ahead and send me in private chat. Just send it to the panelists what your answer is. We factor the numerator and denominator like that to see, hey, that's going to simplify a little bit. Let's clean this up a little bit. I'm trying to isolate b minus a. Let's rearrange that fraction. And there we have it. B minus a ultimately ends up being 1. Now, this is kind of the classic way you'll see the difference of squares, but we can use this template to help us out with other types of problems. Probably don't think of a question like this, just a simple multiplication problem, as being a difference of squares. And I wouldn't recommend that you do so normally, but it's good to kind of train thinking about this way on easier problems so that you can kind of advance to more difficult ones and it's not, so overwhelming. So you can think about 12 times 8 as really being 10 plus 2 times 10 minus 2, which FOILs out into 10 squared minus 2 squared, which of course is 96. Now, of course, we don't do that when we multiply 12 times 8. We probably just have that memorized or can sketch it out pretty quickly. But it's interesting to note that you could do it. You could see 96 as a difference of squares. Let's try that same line of thinking with this problem. 16 times 24. I want you to really force yourself to try this as a difference of squares. We'll get more practice in a moment. Give this one a shot. Maybe we can see that right in between 16 and 24, the average of those numbers is 20. And 16 is just 4 below 20. 24 is just 4 above 20. So really we could write this out as 20 minus 4 times 20 plus 4, or the difference of squares, 20 squared minus 4 squared. 20 squared is 400. 4 squared is 16, and so the difference there should be 384. Now you could do that kind of just the typical 2-digit by 2-digit multiplication pathway, but I'm really trying to get you to think flexibly here. So let's try a couple more, all right? I'll sketch this one out first, and this is quite similar to Joni saving money that we did earlier. 7 is 10 minus 3. 13 is 10 plus 3. That's 10 squared minus 3 squared. That's 100 minus 9, which should be 91. Not should be, it is 91. Let's try that on a couple more. I'll give you a moment to attempt these. Resist the temptation to do these the classical way and really try to do them the difference of squares way. I'll start in the bottom left. And again, try to beat me through these ones if you're doing them on your own. If you're doing them on the recording, just feel free to pause if you'd like more time to work through these. But I'm going to go ahead and get started. By the way, I have actually used this trick on 22 times 18 in an official guide problem to work through an answer choice quickly. So it is useful. I'm not just kind of showing you neat tricks. These are meant to be useful on the GMAT. Let's go to this top right one. Those both look pretty close to 12. And in fact, they're both equidistant from 12. Now, I would say, if you were working through the first two on the left, you could probably do those in your head or kind of the traditional way faster than you do them the difference of squares way, especially if you haven't practiced. But these ones on the right might be a little bit more difficult or might be more efficient options. Or these are options to choose the difference of squares method that might actually be more efficient. And as you get larger and larger numbers, of course, the multiplication traditionally can take more and more time. Those are options where the difference of squares method really starts to kind of see its use. Let's look at this bottom one. 700 plus 11 times something that's 11 less than 700. That should be 700 squared minus 11 squared. Well, 700 squared is just going to be 49 with a bunch of zeros at the end. Should be 4 zeros because I have 2 zeros in 700 twice. Subtracting 121. Well, that's going to be a pretty large number, but it should just be 100 and then 21 less than 49,000 or 490,000. So it's going to be pretty darn close to 490,000, something like this. Yeah, it can be a little easy to kind of mix up your numbers. There's a comment that just came in that says, I did 705 plus 6 times 705 minus 6. 705 plus 6 times 705 minus 6, that would be 711, which is good, but you'd be multiplying it actually by 6 less than 705 is 699. And we're looking for 689 here. So, of course, if you happen to know what 705 squared was, you could use this method to solve 711 times 699. Lots of bonus points if you happen to know what 705 squared is. You could actually use a different quadratic template, not the difference of squares, but you could do like 700 plus 5 times 700 plus 5 to figure out what 705 squared is, and then you'd have to subtract 36 from that. So these things are all related. Okay, you're like, Jeff, why did you make us do that horribleness? And there is a purpose to it. I'm not just trying to torture you. It's because if we get better at foiling out these numbers, all right, to end up at a difference of squares, Okay, 91 is a difference of squares. It's 100 minus 4, 100 minus 9. 396 was a difference of squares. It's 20 squared minus 2 squared. If you can get better at that, you also will get better at doing it the other way, where you can recognize that you're starting with a difference of squares and you're supposed to factor it out. And that's probably what happens a little bit more often on the GMAT. So take a moment and consider the number 891. Can you think of this number as being a difference of 2 squares? It takes a little bit more kind of creativity to see these. Yeah, I'm getting the right answer choice coming in the chat. It's kind of like how, you know, to be really good at division, you have to be really good at multiplication already. Or to be really good at subtraction, you already need to know how to do addition really well. To be really good at factoring, you have to be pretty good at foiling. And so that's basically what we're doing here. Can you see that this is a difference of squares? And it kind of relies on you knowing the kind of back and forth relationship between the previous screen, the questions on the previous screen, and the ones that'll be up on this screen. One suggestion in chat is, let's go back to the blue color, is that 891 is 900 minus 9, which is true. I mean, it's also 910 minus 19, but that's not going to be particularly helpful here because 910 and 19 aren't perfect squares. Let's rewrite this as 30 squared, which is 900, minus 3 squared, which is 9. If you do that, you should be able to split this up into the factored out form, 30 plus 3 and 30 minus 3. 891 is 33 times 27. Aaron, great job. Let's try a couple more. Give yourself a moment to think about, are these numbers on the screen, can I think of them as the difference of 2 squares? I'm going to start doing a little bit of work here, but again, you know, if you're on recording, if you're watching the recording, pause this and see if you can push yourself each step. Can you think of these numbers as the difference of squares? The decimal ones are a little trickier. Last one's probably the trickiest one. I have seen some questions in the official guide that involve pretty ridiculous decimals. So, and you want to solve those via the difference of squares method. So this is a good opportunity to practice that. I'm going to put my courtesy zeros in front for this one. Can you think about how this 4 at the end of all those zeros is a square? There we go. And you'll see that this one's very closely related to the one above it. Just a couple more decimal points, right? You've moved the decimal basically to the left twice, which means you've divided by 100. And so you can see the 1.2 has changed to 0.12. The 0.8 has changed to 0.08. So there's a couple factors of 10 in there. Oh, wow. Thanks for getting through that with me. Let's see how it relates to the problems that were up initially. With this in mind, the stuff we've just done, take a look at these numerators. Can you think about each of those numerators as a difference of squares? Well, they both seem pretty close to 4. All right, so let's use that as our starting point. Again, go ahead and start doing some of the work here. I'll sketch out some of my own notes. Think of this as 9/100. 9/100 is 3/10 times 3/10. All right, so you could do this one with kind of long division, decimal long division. Some people really hate long division with decimals, so if you're not comfortable doing that way, here's another way you could do it, right? The difference of squares method. The fraction on the right, 3.96, well, that's also pretty close to 4, right? That's 4 minus 4/100. Well, if 9/100 was 3/10 squared, 4/100 is just 2/10 squared. And so that would factor into something like this. 2 plus 2/10 times 2 minus 2/10, or 2.2 times 1.8. We can go ahead and rewrite the 3.96 as being 2.2 times 1.8. There go the 2.2s. This whole thing turns into 1.7 minus 1.8. It should be negative 0.1, or B. Okay, so again, you could do this one with long division, just like you could have done Joni's problem with some smart numbers. You want to practice multiple ways to do it, because on the GMAT, you want to be kind of as flexible a problem solver as you can. On this next one, the one with the rectangle, I am not 100% sure that you could do this multiple ways other than by kind of brute forcing all the possibilities, which is just going to take too long. So let's consider what this is saying. A rectangular field has an area of a bunch of square meters. The length and the width of the field, you can call them L and W. We're doing that so we can find out some rules about them. L and W are integers, okay. And L is greater than W. That seems kind of arbitrary right now, but okay, thanks. What's the field's perimeter? Okay, maybe I understand why L is greater than W, because these things seem to be restricting different measurements of those dimensions. But like, you could have a rectangular field of 3,551 potentially a lot of different ways. Like, you could have a really skinny field that has a width of 1 meter and a length of 3,551 meters. That would give it an area of this and, you know, one particular type of perimeter. But maybe there are some other numbers that multiply to 3,551, and thus you could have different options for your length and width other than 3,551 and 1. So let's take a moment to think about this number. And if you've been paying attention for the last 40 minutes, think about this number as potentially a difference of squares. How could 3,551 be written as a difference of squares? Do you know any perfect squares in the ballpark of 3,551? And yes, 3,600 is a good one, right? 36 is 6 times 6. 60 times 60 should be 3,600, okay? Just a good one to know. It's also the number of seconds in an hour, because there are 60 seconds in a minute and 60 minutes in an hour, okay? So 3,600 is a good number to know. And yeah, 3,551 then could be written as, well, it's a little bit less than 3,600. In fact, it's exactly 49 less than it. And there you have it, 2 perfect squares. Let's go ahead and factor this. 3,600 is 60 times 60. 49 is 7 times 7. So remembering our template, if 3,600 is a squared and 49 is b squared, then b is 7 and a is 60. One should get the addition, one should get the subtraction. Oops, let me erase that. Got a little carried away there. This should be 67 times 53. So you had a couple options initially. 3,551 could be 1 times 3,551. It could also be 67 times 53. Could it be anything other than those? Are there any other integers you could positive integers that you could multiply to get 3,551? Well, you'd want to see kind of all the potential building blocks or factors in 3,551. Here's a couple that we've started with. Can you break down 67 or 53 any more? And no, you can't. They're prime. Yeah, really good stuff. These are prime numbers. So the only kind of possible ways you can break up 3,551, this field, is to have a really skinny field, 1 by 3,551, or a more kind of, you know, typical rectangle we think of, where it's not really skewed, 67 by 53. Those are the only ways to do it. So if those are your options, 1 and 3,551, or 53 with 67, and you know that L is greater than W, you only have these 2 options. Statement 1, W is greater than 30. can't be this option. So it's got to be this one. You have a W and L, you could figure out the perimeters. Statement 1 is good on its own. L is less than 118. Well, L can't be 3,551. So it's got to be this combo. And again, from those, you could find the perimeter. So this one's actually D, right? Answer D here. With either statement, you'd be able to solve this one. Of course, there's a lot of steps along the way to being able to get there. Another kind of opportunity for me to make a point about data sufficiency. If you see a question like this, or a question that looks really difficult, and you're not sure how to solve it, and therefore what the answer is, in those cases, I would never pick answer E, right? Never say that there's not enough information because I don't know how to do it or I'm overwhelmed. E is reserved for those moments where you have like proven there's not enough information. And as you can see here, there's plenty of information given to you if you know how to look for it. So on the other end of the spectrum, the answer to this question is, oh, there's like an abundance of sufficient information on this question. So the answer would be the opposite of E. There's just so much sufficiency here. So just a kind of an opportunity to remind you about good data sufficiency habits. If you look at a question and are overwhelmed by it because it seems complicated, don't pick E because you don't know how to do it. For me, if I am unsure whether or not a statement is sufficient or not, I'll usually just assume that it is and that I'm not clever enough to see why. I want to be very sure about a statement being not sufficient for me to cross it out. All right, hey, that was good stuff. We're not done yet. I have maybe a couple extra problems here, maybe just one or two more to kind of build off this in another way. But yeah, how about that? Those are some tricky questions, and I would say it's kind of tough to see that all of these questions are kind of related to this idea of difference of squares from the outset. But if you kind of hone these recognition skills, you might be able to take a look at 3.91 and 3.96 and see, those are pretty close to 4. In fact, they're just a little bit less than 4, a perfect square away from 4. Same thing with this one. 3,551 is not a number you see every day. But if you recognize that it's close to 3,600, and in fact, it's just 49 less than 3,600, you've got some insight into the problem. Here's maybe a problem you wouldn't use difference of squares on, but you clearly could, kind of showcasing the versatility of this thing. Maybe take a look at a couple more problems that the GMAT could throw at you that have to do with the difference of squares. Take a moment and think about this. At least here, kind of the template for the difference of squares is kind of thrust upon you, right? So you don't have to do that extra step of kind of figuring out that this might actually be a difference of squares. It's kind of suggested to you by the format here. Go ahead and take a moment and work through this one. I'll give you about a minute or so. Let's try to work through this one a little bit. Now that we kind of know that 3 to the 6th and 2 to the 6th seem like squares. Well, I guess 3 to the 6th is 3 to the 3rd squared. And 2 to the 6th, excuse me, yeah, 2 to the 6th is 2 to the 3rd squared. So, that seems like you could say, hey, 3 to the 3rd is A, 2 to the 3rd is B in this template. So this would be A squared minus B squared. Let's keep working there. That should be able to factor right into A plus B, A minus B, which should be 3 to the 3rd plus 2 to the 3rd times 3 to the 3rd minus 2 to the 3rd. Now, 3 to the 3rd and 2 to the 3rd, you're going to have to know, okay? The GMAT won't ask you to know what like 2 to the 19th power is, but 2 to the 3rd is fair game, as is 3 to the 3rd. 3 to the 3rd is 27, 2 to the 3rd is 8. And so this turns into 35 times 19. So apparently 3 to the 6th minus 2 to the 6th is 35 times 19. I got to figure out how many positive integers, single digit positive integers, are factors of whatever this number is. You could multiply it out. Like you could know that 3 to the 6th is 729 and 2 to the 6th is 64, which should give you 665. But I think like you don't actually need to go that route. Once you know that this particular expression is 35 times 19, you could say, oh, that's the same as 5 times 7 times 19. So clearly 5 is a factor. 7 is a factor. Is the answer 2 then? If 5 and 7 are both factors? Are there any other single digit positive integers that would be factors of whatever this thing is, or 665? Don't forget about 1. 1 counts as a factor. It seems kind of trivial, but it technically counts. So there are actually 3 of them here. Okay, nothing else above 7. That's single digits. Nothing in between. You could take a look. You could kind of number theory some of this out. 3 to the 6th is a bunch of odd numbers multiplied by each other. 2 to the 6th is a bunch of even numbers multiplied by each other. So if you kind of like generalize that, this would be some big odd number. This would be some even number. So your answer would be odd. And then you'd say, well, I guess 2 can't be a factor of an odd number. Neither can 4, 6, or 8. And so you could like get a little bit closer that way. But I think kind of in general, the best way is to factor it out like this. 5, 7, 19 go into this total. Don't forget about 1. So 1, 5, and 7 would be your 3 factors. I have a question that's come in, and it says, if single digit was not part of this. This is a good question, and maybe we can just kind of take a brief tangent into here to address it. If single digit were not part of this, how many positive integers are a factor of this expression? Would the answer be 4? Because then you'd have like, I don't know, an extra, you wouldn't have that limitation because 19's in play. And I would say, well, it can't be 4 because in addition to 1, 5, and 7, you have 19 and you also have 665, like the biggest number, the entire thing is a factor of itself. So the answer couldn't be 4, and in fact, the correct answer to that wouldn't be on the list. I can show quickly how you could solve it, okay? If you know that the factors of this whole thing are 5, 7, and 19, and those are the only prime factors, the way you could conceive of it, I'll show you 2 ways, is, well, I could choose pieces from 5, 7, and 19 and combine, you know, pieces of those options to get to kind of portions of the total. So I could choose just 5, all right? 5 would be a factor because if I divided the expression by 5, I would get the remaining 7 and 19. I could choose just the 7, right? And so if I divided this whole expression, which is 665, by 7, well, I should get the remaining 5 and 19. Of course, then I could choose 19 as well, okay, and have the remaining 5 and 7. And so what's actually happening there is I'm breaking 665 into sets of factors, 5 and 7 times 19. So 5 is a factor, but so is whatever 7 times 19 is, 133, I believe. 7's a factor, but then of course so is its kind of, complement, the missing 5 times 19. So there would be 2 more factors there. 19's a factor, but that would mean the missing 5 times 7's a factor, or 35. And so there's 6 right there. And then you don't want to forget about 1 and the total. So there would actually be 8 factors of this whole thing. I'll show you one other way. That's kind of a cool way to think about this. And it has to kind of do with combinatorics, which I know is a very scary word for a lot of people studying the GMAT. It's still kind of scary for me. And that is when you get to 665, okay, you multiply 5 to the first times 7 to the first times 19 to the first. And if you want to think about all the kind of little factors of 665, you want to consider that you didn't have to choose the 5 and the 7 and the 19. You get to kind of pick and choose which pieces you want. And so a way of thinking about that is you have 2 choices for how many 5s you want. You could choose the 5 or not the 5, right? You could choose to have 1 5 or you could choose to have no 5s in your factor. Same thing for the 7. You could choose either to include the 7 in your factor or not choose the 7 as one of your factors. So there's 2 options there. And then you also have the choice, the yes/no choice of, do I want to include a 19 in my factor? And, oh, that shouldn't be a 2 there. That should be that shouldn't be a 19 in the blank. That should be a 2. That's what happens when I go off script. So you have 2 options for including a 5, yes or no. 2 options for including a 7, yes or no, and 2 options for including the 19. And so what that means is you have a total of 8 choices, okay? And those would align with the 8 choices that I had previously just listed with the circles. I'll do one quick problem that kind of addresses all of that. So pay no attention to the words on the screen. If you wanted to quickly figure out the number of factors in, let's say, 120, how many factors in 120? You could list them all out. That would be doable. But another way you could do it is to break 120 down into its prime factors, okay? And so let's see, what's 120 made of? Well, it's made of 2 and 60, and 60 is then made of 2 and 30, and 30 is made of 2 and 15, and then 15 is made of 3 and 5. And so what that means is 120 is really 2 to the third times a 3 times a 5. Now, if you're trying to figure out how many factors there are in 120, think about how many options you have for each of those prime factors. How many 2's do you want to consider? Well, I could use 0, 1, 2, or 3 2's. So there's actually 4 options for how many 2's I want to include. There's 2 options for how many 3's I want to include. I could choose 1 or 0 3's. And I could choose 1 or 0 5's. So I have 2 options there. 4 choices for how many 2's, 2 choices for how many 3's, 2 choices for how many 5's means you have a total of 16 choices for what factors you want to include or total factors. Yeah, kind of a cool, Aaron, thanks for the question. Kind of a cool little aside there. Ways to figure out how many factors in any number based on the prime factors. This is also a way that you can prove why perfect squares only ever have an odd number of factors. It's because, well, perfect squares should have an even number of each prime factor that go into it. And if you have an even number of them, don't forget you can also choose none of them. So there will be an odd number of choices for how many of each of those prime factors you want to include. So this will be an odd number, this would be an odd number, this would be an odd number, and your product would then be odd. That only works for perfect squares. Cool, guys, that was a really fun hour. I'll tell you what I'll do though. I have a couple more questions that I just kind of came up with that I will put on the screen. If you're watching on recording, you know, take as much time as you want to do this. But let's see. Here's a question that I think you could solve a couple ways. You could solve it with quadratic. You could just factor 1015 if that's what you like to do. Or I would challenge you to try the idea of difference of squares here. Go ahead and pause it now if you don't want a hint. If you haven't paused it by now, I assume you want the hint. One way to think about this is consider where the average between the two numbers lies. Okay, the average between the two numbers should be 3 above one number and 3 below another. You could use that to solve this with the difference of squares. And here's another one that I came up with. If p is a positive integer, what's the greatest integer that must be a factor of this? You could test out some numbers and come up with a factor you think is common to all of those results. Or I would challenge you to prove what it is. I will give you a moment to pause it here. And I will tell you, it's pretty easy to prove that this quantity will always be divisible by 12. Okay, I'll say it's, you know, relatively easy to prove that it's always divisible by 12. However, it is possible, though more difficult to prove, that this will always be divisible by 60. So it's also divisible by a 5, which does not seem immediately apparent, but I will challenge you to try to figure out how you can prove that this quantity will always be divisible by 5 as well as 12. So I think we'll call it there. I will stick around if people have some questions. I'm going to cut the recording off here. If you watched the recording, thanks so much. I hope to see you at one of these another time when it's live, but thanks for watching the recording. If you are